This question is from the GATE Physics paper 2021. This is a numerical answer type 2 marks question and the topic of the question is electromagnetic theory. So the question is, consider two concentric conducting spherical shells as shown in the figure. The inner shell has a radius small a and carries a charge plus q. The outer shell has a radius small b and carries a charge minus q. The empty space between them is half filled by a hemispherical shell of a dielectric having permittivity epsilon 1. The remaining space between the shells is filled with air having the permittivity epsilon naught. The electric field at a radial distance small r from the center and between the shells, that is r greater than a but less than b, is, four options are given. Option A is q by 2 pi times epsilon naught plus epsilon 1 times r squared along the r cap direction everywhere. Option B, q by 4 pi epsilon naught multiplied with 1 by r square along the r cap direction on the air side, and q by 4 pi epsilon 1 multiplied with 1 by r square along the r cap direction on the dielectric side. Option C, q by 2 pi epsilon naught multiplied with 1 by r square along the r cap direction on the air side, and q by 2 pi epsilon 1 multiplied with 1 by r square along the r cap direction on the dielectric side. Option D is q by 4 pi times epsilon naught plus epsilon 1 multiplied with 1 by r square along the r cap direction everywhere. So let us see the solution part. According to the question, we are given two concentric spherical shell. The inner shell has the radius small a and the outer shell has the radius small b. As the spherical shells are conducting, the plus q charge will be uniformly distributed over the surface of the inner shell, and the minus q charge will be uniformly distributed over the outer shell. The empty space between the two shells is half filled by the hemispherical shell of a dielectric having permittivity epsilon 1, and the remaining part is air having permittivity epsilon naught. Now the dielectric in the region between these two spherical shell, that is hemispherical part, will be polarized, and because of the polarization there will be formation of bound charges in this dielectric medium. Now the displacement vector in the air is given by d naught vector equals to epsilon naught times electric field vector E, and in dielectric it will be d1 vector equals to epsilon 1 times E vector. We only have the information about the free charges, not the bound charges according to the question. So we will use the Gauss law in terms of the d vector, that is surface integral of the d vector is free charge enclosed by this surface. So according to our schematic, the closed surface is the dotted line. So the free charge enclosed by the surface is only plus q. So we can write this surface integral as d naught times 4 pi r square by 2, which is the surface area of the closed surface in the air region, that is 4 pi r square by 2, plus d1 times 4 pi r square by 2, which is also the surface area, that is the half of the spherical surface area in the dielectric region, and the free charge enclosed by the surface is plus q. So we can take this 4 pi r square by 2, that is 2 pi r square, as common, and we will have 2 pi r square times d naught plus d1 equals to q. We can write it as 2 pi r square times epsilon naught e plus epsilon 1 e, so which is basically our displacement vector d naught and d1, equals to the free charge enclosed by the closed surface, that is plus Q. So we'll take E, the electric field, as common. So we'll get 2 pi r square E times epsilon naught plus epsilon 1 equals to Q. So our electric field is Q by 2 pi epsilon naught plus epsilon 1 times 1 by r square. The direction of the electric field in the region r greater than a but less than b region will be along radial direction, that is r cap direction, as the charge distribution on the spherical shell surface is spherically symmetric. So the electric field vector in the region will be q by 2 pi times epsilon naught plus epsilon 1 times 1 by r square along the r cap direction. So our option A is correct. So according to our solution, the electric field at a radial distance small r from the center and between the shells, that means in this region, is option A, q by 2 pi times epsilon naught plus epsilon 1 multiplied with 1 by r square along the r cap direction, that is radial direction, everywhere.